So this week we're very glad to have Salim Tayou from Dartmouth and Affiliation to tell us what Kudla's modularity.
Oh, great. Thanks. Thanks, Naomi, for the introduction. And thanks for the invitation. It's great to be here, as always, Darius. So today I would like to give you updates on the conjecture that Kudla made 10 years ago regarding modularity of special cycles in unitary Shimura varieties and other Shimura varieties with today. I will specifically talk about unitary Shimura varieties. So let me just introduce the setup. It's okay. Will be quadratic imaginary field. Okay will be its ring of integers, and then assume that I've given an embedding of k into C. Now let's L and H be a Hermitian lattice. So L is a projective OK module of rank n+2. And H is a Hermitian pairing on L, which has signature n+1, comma 1. Okay. Now, associated to this data, we can construct a unitary Shimura variety. X is a D mod gamma. So the unitary Shimura variety associated to the group UN+1, comma 1. And okay, so let me just give a brief recall what's this dr and this gamma are, and they're very easy to describe in this case. So D, that these are just ball quotients, but they also can be seen as just like lines inside LR. So this LR acquires the structure of it's a C vector space, and then these are like complex lines. And the extra condition is that the Hermitian pairing restricted on this line is negative. The norm of this line is negative, a generator. Gamma is just some arithmetic subgroup inside the unitary group that preserves the lattice. In fact, for this talk, let me just choose as a neat arithmetic subgroup so that now this quotient here is just a smooth quasi projective variety that can be compactified by adding, in fact, simply one of the only points. That's the Bailey-Borel compactification. Let me say a few words on that later. Now, this variety, in fact, let me just make a remark, admits also a modular interpretation. You have to set it up correctly, but so these are moduli spaces of abelian varieties. C, let's say, of abelian varieties, dimension n+2, and that admits complex multiplication by OK, and for which the action of OK on the, so if you have like any geometric point, like a complex point, the action of OK on the Lie algebra of A over, so this is a complex Lie algebra decomposes as a sum of n+1 copies of C, and 1 copies of C. And so the action of OK here is just via that embedding that we have chosen. Give it a name, iota. And the other copy is iota bar. Now, this unitary Shimura variety has a family of special cycles defined in every codimension in the following way. So, anytime you take a vector lambda in L, you can consider d lambda subsets of D of lines that are orthogonal with respect to the Hermitian pair H to lambda. And then, if you're given an integer m of least 1, you can take Cm, the union over all these d lambdas, for which h lambda is equal to m. Take the quotient by gamma. This is a divisor in this Shimura variety, d mod gamma. In fact, each of these smaller d lambdas are just defined using smaller copy of the unitary group. So this will be defined by a UA gamma 1. And now you can intersect many of these to get higher codimension cycles. So more generally, if you have an integer g at least 1, and then m a g by g Hermitian, let's say semi-positive definite matrix, then I can define the following cycles z of m, which are going to be now the union over all tuples of g vectors, lambda 1, lambda g, and L, whose intersection matrix is equal to this fixed matrix M, and I intersect the g copies of this d lambda i's. So d lambda I lambda j. Again, and take the quotient by gamma. And this defines an algebraic cycle in X. Now, if M is positive definite, it's going to be of codimension exactly G. In general, it's going to be the codimension equal to the rank of this matrix. So from maybe like there's a very nice construction of these cycles if you adopt the modular construction, which is, so the modular interpretation, at least for this, let me just say it for Zm, and the higher case is the same. So this will be the abelian varieties that are isogynous to a Cm elliptic curve times an abelian variety of dimension 1 less. So dimension m plus 1. And this is Cm by OK. And on this B, you have similarly the same condition on the signature, or like what is embeddings, instead of being now n plus 1, it's going to be n at 1. So you can see these are also constructed using a UN1. And more generally, for the ZMs, you can, abelian varieties parameterized by this bigger ZMs will be just the ones that splits off like G, Cm elliptic curve, and then an abelian variety B of dimension, n plus 2 minus G. So they have a very nice modularity. Okay, now the following, like Kudla and Millson, we introduced the following data series, generating series, which is the sum over all the matrices M, which are G by G, of the classes of this cycles, the N's, Q to the power M. Okay, so I need to tell you exactly what this means. So the classes of the ZMs will, if ZM is positive, or like the matrix M is positive definite, let me just take this cycle, the class of this cycle, and if not, I will just copy it with the first chain class plus a specific one bundle, L to the power G minus the rank of M. So this is to account if the lambda i's are not, if n is not positive definite, there's going to be some excess intersection. And so this like extra term is accounting for that. And this L is the dual of the topological bundle on X. So you see from this description of D as a set of lines, you can embed it into the projective space of LR. And LR is a C vector space. So it has a topological bundle restricted to D and take its dual. And it coincides with the normal bundle of these cycles D lambdas in D. So that's why this expression makes sense. Now, what is e to the power m? So now I will consider a variable tau in the Hermitian upper half space. And so this is the set of matrices, complex matrices, G by G complex matrices, such that when you do this operation, Z minus Z bar transpose divided by 2I. This is Hermitian and positive definite. So this is some analog of the Siegel space, which maybe you're more familiar with, but this is a Hermitian symmetric space for the split unitary group U, G, comma G. Now this Q to the power m is simply exponential of 2 pi I trace of tau times m. Okay, so Kudla and Millson proved the following amazing theorem, is that this generator series is a holomorphic modular form, Hermitian modular forms in the variable tau. Theorem. This is due to Kudla and Millson. 80s is that theta of tau is, maybe I should say something here. As written, this generator series makes sense in the Chow group of cycles of codimension G and X, the double bracket Q. But what they prove is, in fact, this, and if you take the cohomology classes of these cycles, then it becomes a Hermitian modular form, Hermitian holomorphic modular form of weight n plus 2, and the level is some congruent subgroup gamma tilde inside like the integral split unitary group UGG concept. And of course, this is in cohomology. The meaning when you take the classes in the H2G of X with say with R coefficient. Okay. So this is like an instance of what's called the geometric theta lift between, and the dual reductive pair here is U n plus 1 1 and U G comma G. And so Kudla made the following conjecture. Let me like they come reading the package. So the first conjecture, of which I'm not going to say anything today, is that this modularity holds in Chow. mean, except like some very few results due to Shia, this is a partial result. This is still wide open in general. And the second one is, well, this unitary Shimura varieties can be non-compact. And then what happens if you take compactifications of this Shimura variety? So in conjecture that there exists some compactification, which is smooth, projective, such that well, when you take the Zariski closure of these cycles, there's some way to take a correction by boundary cycles in a way that you restore modularity. So there exists some correction z tilde m, which is going to be Zm plus some boundary cycles. And so this is now the Zariski closure in X. X bar. Such that the resulting generating series is a holomorphic permission boundary. Is holomorphic permission modular form the same weights and level.
Do you know why Kudla conjecture is number 2?
Number 2?
Yes.
So the first observation is that the way Kudla and Millson proved this modularity statement is by noticing that the cycles admit some Poincare dual forms that like fit well into like the theta correspondence machinery. And in small codimensions, they happen to be integrable, and so they like L2, and so the generator series will also be a modular form in the L2 cohomology, which is the same as the cohomology, the Betty-Borel.
So is the issue really about the boundary behavior?
Yeah. So this modular, this dual, this Poincare dual forms, when you consider them in a compactification, well, you have to regularize them in some ways that naturally make appear some boundary cycles, and so.
Yeah, as I remember, even Kudla and Millson are not very, they leave things projecting to cuspidal cohomology, right? In their original paper. Are you saying that it was related to that issue that he came to the second conjecture?
Well, and I think in the original paper they formulated the conjecture in H2G, like just singular cohomology, right? Like with the round cohomology, and the content of the statement is wherever you pair it with a cycle that's entirely supported in the boundary, supported in the interior, like a compact cycle in the interior, you get a modular form. But it's not clear that if you pair it, let's say you just integrate them over the whole thing, you will get a modular form. And so so my understanding, that was like the motivation is to try to understand like this limit behavior of these Kudla-Millson forms. And
can you remind me, in the theta lift, this is a range in which the integral doesn't converge, I assume. They have to analytically continue some. Yes, no.
So I mean the construction is really, I don't remember it using any Eisenstein series, right? They use like explicit Poincare dual forms.
And things converge directly, like us in the Siegel wave formula. Often that's one of the things that I think Kudla did, was to regularize. So that's
right.
Needed.
Yeah, that's not needed. Yeah, that's not needed, because like somehow they're only pairing with cycles that are compact, like compacts that are supporting the interior. If you were to compute, let's say, the volumes of these cycles, then that would be maybe a region where things don't work well. Right. I mean, there's definitely something happening with the decomposition of the cohomology of the unitary Shimura variety into the cuspital and the Eisenstein part that should see like what these boundary cycles are, but yeah, that's something like I don't myself don't understand that very well, but yeah. So yeah. But at least like from the point of view of you just like follow the construction of the Poincare dual form. It's not if you try to understand it like the class it defines as a current on the compactification, it will not only represent the special cycle, it will represent the special cycles plus some boundary cycles. Right. Yeah. That's up. All right. So the theorem I'll explain today, this is joint work with François from last summer, is that, well, there's a canonical compactification we can take for this portions, which are the toroidal compactifications. In this case, they really don't depend on any choices.
There's not like a fan or something?
No, yeah. In this case, it's really simple because like where there's a canonical choice of thing you have to do. They're all one-dimensional. Like the fan that you have to choose is just in a line. So there's no canonical choice you can do. Of course, when you're in a line, you can choose either right or left, but then the positivity tells you which one you have to choose. So we can just take work with this compactification, and there, Kudla holds Kudla's conjecture for 2 holds in homology and up to the middle degree. So for G less than like strictly less than n plus 1. So the dimension of this of the Shimura variety is n plus 1. The boundary is within the dimension n. So if you are in this range, then we are able to construct like explicitly some correction with boundary cycles. In fact, as a corollary, if you just take now the Zariski closures of this is the n q to the power m, this type of function, in fact, have a name, and they are what are called quasi-modular form. Meaning that you can, there's like 2 statements here. There's Kudla's conjecture, and this is the second statement, saying that you can complete them in a non-holomorphic way, in such a way that transform like a modular form. So kind of non-holomorphic.
The non-holomorph is just sort of like on a constant term. It's some simple kind of norm. It's not.
In codimension 1, yes, but in higher codimension, it's like not simple. I will explain like a main example of what that should look like.
So what is Z of M bar?
Oh, so I'm taking the Zariski closure. I mean, I could
Zariski closure.
just the Zariski closures, yes. Yeah, in this compactification. Okay. All right. So let me say a few words on the proof. Oh, let me say also like what previously was known. So for G equal 1, that I mean even in child 1, even like arithmetic child 1, you insist on like defining all of this data over like some number fields and consider arithmetic child groups. This was known by work of Brunier, Howard, Kudla, Rappaport, and Young from 2020. And then for G, like maximal top dimension,
Gn+1. So for 0 cycles, this was known, or this was proven quite recently by Brunier, Rosu, and Demo from 24. Okay. Questions?
What does the boundary structure look like?
Okay, so that's where I'm headed to. So let me just give some ideas of the proof and the construction. So first, the natural compactification of this Shimura variety is the Bailey-Borel. And the Bailey-Borel is in fact just a disjoint union, a finite disjoint union of points that are parametrized by rank 1 sub OK module of L. So L I is primitive rank 1 and isotropic. So up to gamma action, there are finitely many such like one primitive isotropic subspaces of L. And the Bailey-Borel is just obtained by adding this finite collection of points. So it's singular, is for n high enough. And the next one that we will work with is the toroidal compactification. And this also happens to have a very simple structure, which is as follows. So X is compactified with X toroidal, and then the boundary is a disjoint union, again, over all this rank 1 isotropic primitive sub OK modules of L. And then there are some boundary components, let me call them BI. So these are divisors, smooth divisors. And so it's, in fact, here the boundary is really just a disjoint union of smooth divisors, and each divisors live over the corresponding point in Bailey-Borel when you map this to Bailey-Borel. And these BIs are also very simple to describe. In fact, there are going to be just if I call E C mod OK, this CM elliptic curve, again using the fixed embedding that I had of the number field into C. This is just the Serre tensor construction of E with phi per mod I tensor over OK. Okay, so if I per mod I happen to be free of rank n over OK, this will be just isomorphic to e to the power n, just like an n-fold copy of a CN elliptic curve or a CN elliptic curve. I mean, in general, I per mod I is not going to be free OK module. There's going to be some class number involved, and so it's almost like this. So these are the boundary divisors. Okay, now the first lemma that's saves the day is this very general lemma of algebraic variety. If you have smooth pair, so X smooth projective and D is a smooth divisor, and you assume that the normal bundle of D, or like the dual of the normal bundle is ample on D, then the homology of X can be generated by the homology of the complement and the homology of the divisor, which this map here is surjective. And in fact, this is like really the bottleneck in the whole proof, is that this holds only up to the dimension of the, which is, let's say, divisors with dimension of X minus 1. So this is really where all the condition on the codimension appeared in this theorem. There's some way to avoid
prove this in higher for any k, at least in our setup, then we can prove the theorem in any for any g.
I mean, this, how does your Z bar intersect BI, or maybe this is something you'll tell
I'm gonna say it right here, yes. Okay. And the proof of this lemma, as you can imagine, is really standard tools in topology and algebraic geometry. You have the fact that this ample, I mean, in our setting, that's true because the BIs are contracted to points in the Bailey-Borel, so it implies the normal boundary example. And so, I mean, here the proof is just using my Ritteris and then Kiesen and hard left sheds. So it's not fun. Yeah. Okay. Now, the second step is to understand how the special cycles intersect the BIs. So how do these ends intersect the BI. And so why is that? Well, so let me first say why we want to do that. Now we want to prove modularity and cohomology. So each time I take a cycle in, maybe I should have given this a different name. Let me call this Y. It's completely independent. So each time we take a cycle in the homology, let's say in degree 2g of Y, I know by this lemma that C can be decomposed as sum of two cycles, maybe in a non-unique way, where the cycle C1 is in the homology of, I should say X toroidal, where this H2G is in the homology of X, so it's supported inside X, and then C2 is in the homology of the boundary. Now the boundary is a disjoint union of these BIs. And so this is just the direct sum over all like this I of the homologies of these BIs. So another way of saying that the generating series is a modular form using Poincaré duality is that whenever you pair it with a cycle, so I want to understand, like I'm taking this Zariski closure, I'm pairing them with a cycle C, that I can decompose along that sum as Z paired with C1, and then Z paired with C2. Let me add Q to the power M, Q to the power M, Q to the power M. So this is the generating series I want to analyze. Understand its modularity, quasi-modularity, and all of that. When you pair it with a cycle which is supported in H2G, so in the interior of X, this is like you directly invoke Kudla and Millson's theorem. That's implied that this is a Hermitian modular form. So there's nothing to do there. So the whole analysis happens at the boundary. So we want to understand how the special cycle Zm intersects C2 when now C2 is entirely supported in the boundary. And so this intersection will happen in the boundary. So we want to know how does Zm intersect this boundary BI. It turns out that the answer is very simple. So first I will call J I third mod I. Now with this pairing H, like that they have from the beginning, H becomes positive definite on J. Okay, so this boundary components BI, which is this becomes I tensored with J over OK. Now the cycles Zm that will intersect the boundary will in fact be parameterized by elements in the, like in codimension 1 at least. Every time I have a vector lambda in J, I have a natural pairing from E tensored with J to E, where I just pair on the second factor with lambda. Okay, using H.
So if, I mean, these are just an element on an elliptic curve, an element on the lattice, and pair them with lambda, I get an element in OK. And I know how to multiply an element in the elliptic curve by an OK element, so I get an element in here. Another kernel, this is Z lambda, all in Z lambda for a reason. So the limits of the ZMs, so intersected with the BIs, are simply the sum over all the lambda 1, lambda j in this positive definite lattice J, whose intersection matrix is equal to M. And then I just take the intersections of this dimension 1 divisor that I have just defined. This is some type of theory of special cycles on this very particular type of abelian varieties that are totally just a product of elliptic curves. But to remember the positive definite lattice you started with. Okay, so if M happens to be not positive definite, then I'm allowing, I mean, this is just going to be 0, and I'm perfectly allowing that because if you think about the generating series of Kudla and Millson, like this Hodge bundle will just restrict to 0 to the boundary, so they naturally die. So I'm also want to kill them here. And so somehow, like only the term where M is positive definite will matter. So now
Are you saying that in the sum there, the constant term is always 0?
Yes. Yes, and I'll yes. And I'll say why in a second. So okay, so now these are the special cycles on the boundary. I mean, in fact, the first lemma is really to follow what Kudla and Millson did in the interior part is to construct Poincare dual forms for this ZMs. And so, in fact, there exists a polynomial function from this JR to the power G. So this is like, so J is this lattice of dimension N. Take the real, like the tensor into it R, and then take G copies of this lattice. So there's a polynomial function to the space of GG harmonic forms on this E tensor G over, okay? And so this is a polynomial function. So this is a finite dimensional vector space, of course, it is a space of harmonic forms. Such that if you choose any lambda 1, lambda G in the integral lattice, then P of lambda 1, lambda G, the cohomology class of the differential form, is equal to these special cycles that I have defined here. So this, so what this lemma does, in fact, is just constructing explicit Poincare dual forms to the limit of the special cycles on the boundary. Now, furthermore, these polynomials have a very nice invariance property under change of variables. So they satisfy the following condition. If you take any matrix, like GLGC matrix, then and you act on a tuple of G vectors, then you call it lambda underlying part by A, then this transforms as P lambda bar times the absolute value of the determinant of A squared. So this is a very strong homogeneity condition on this polynomials. Okay,
That's GLG, right?
GLG, yes, yes. So the like acting on the right on this lambda one lambda j. So just yeah, you're not changing the spans of the lambda height. Okay. Now, okay. So now the consequence is that when you're taking the intersections of the ZMs with this topological cycle C2, Q to the power M, then this becomes just some type of theta series. We're summing over all the lambda 1 lambda j's, and this lattice G, J, some G and J, J to the power G of the integral over C2 of this differential form, P lambda 1, P lambda J, Q to the power N. Okay, great. So and of course, you take a homogeneous differential forms in the lambda i's, you integrate it against the cycle. So let me call this polynomial here BC2. BC2 will still be a polynomial on GR to the power G, now valid in C, and it satisfies the same homogeneity condition. So let's call the space of such polynomials, like the polynomials that satisfy all these conditions here. I will call them F and G, the space of such polynomials. N refers to the dimension of M, and G is how many copies of M I am taking. The space of all these polynomials, in fact, is finite dimensional. As you can see, I mean, this homogeneity condition imposes finite dimensional. In fact, its dimension is N chooses G squared. The computation. And to any such polynomial now, you can construct its theta series. So take any polynomial P in F and G and form its theta series by summing over elements of this lattice M. Q to the power intersection matrix. Should have said here, it's the intersection matrix of this lambda axis. And say here. Now, I mean, the classical theory of theta series tells you if P is harmonic, then this is just a holomorphic form on the nose. If P is harmonic, then this is a holomorphic Hermitian modular form. And if, well, if P is not harmonic, then you can still say something, and this is in the orthogonal case appeared in some papers of Freytag, and then unitary case in papers of Shimura, is that the space GR, so has like this Hermitian form, and there's like this associated unitary group. So there is an invariant Laplacian. delta on this to the power g. So invariant under the action of the unitary group of J. And instead of taking this P, if you take P sharp, lambda 1, lambda g, and you apply exponential minus Laplacian divided by 8 pi, apply it to P. If you do it like this and construct this new polynomial, then the generator series of this new polynomial, P sharp, transforms like missing something. So I have to. So this is really explainable by their representations, but let's just say too much word about it. So let's call Y the.
So what's the magic about that ether minus Laplacian?
What?
What is that magic number there?
Yes. So let me write the theorem and then say what's magic about it. So you can we just write in the correct order. Yes, so I can. So Y is this tau minus tau bar divided by 2I. So I weight by determinants of Y inverse, and then I sum over all the lambdas in g to the power j, exponential minus Laplacian 8 pi, apply to P, and then lambda bar times.
Seems like you would want to decompose P into its eigenspaces, taking some specific combination. Is that right?
Yes, I will do that in a second too. Yeah, absolutely. So, what's the reason why we introduced this P is that, well, to prove that something transforms like a holomorphic modular form, which is the content of this theorem. Okay, so let me just write the theorem. This is due to Freytag and Shimura.
Yeah, it was joint.
What? Not in a joint. Freytag did it in the orthogonal case, and Shimura really in the unitary case. Yeah. So this is transforms like a Hermitian modular form of weight n plus 1, n plus 2, and some level. Okay. Okay, so two remarks. The first one is the reason why this works when P is harmonic is that let's just relies on the Poisson summation. That's when you do the theta series and like you apply Poisson summation, the Fourier transform happens to be exactly the same thing just by integration by parts, and you recover P again once you do the Fourier transform, and so that's why you get it's a modular form. If it's not harmonic, then it's not true. But what's amazing is that it's gonna be true for this new polynomial. So this new polynomial will satisfy Poisson summation. That's why you get.
Sorry, going back for a second. So you didn't really have to use harmonic forms, right? Surely you could have just done that part of the analysis algebraically.
Yes, it's
Okay.
possible.
Okay.
Yes, like you could map. So this is actually something in progress with the Ben Howard. Like you can construct this polynomial from J to the Chow group of the boundary.
Okay. And this maybe second question is, there would be a parallel story. Rather than start with a CM curve in tensor with a Hermitian lattice, I could have started with any elliptic curve in tensor with a quadratic lattice, and there would be a parallel story.
Absolutely.
Okay.
So that's in fact again what happens in the orthogonal case.
Right. Although it does, I guess there's no corresponding interpretation or
Interpretation of
like this e to the whatever it was came as the boundary of the unitary Shimura variety.
yes.
In the orthogonal case,
You can take the universal elliptic curve, like which is like if you take, I mean, elliptic curves either CM or non-CM, but the non-CM ones, then you're just working with universal elliptic curve, and over you do a modular curve, and then you're tensoring it's a Kuga-Sato variety over the modular curve. And then the special cycles there in the orthogonal case limits to the same thing. It's during the work in progress. I don't want to say it.
Okay, I'll ask you about it later.
Yeah. Okay, so that's the first remark is that why we take these exponential Laplacians, and then the second remark is this exponential of this Laplacian will because P is a polynomial. In fact, this is also a polynomial because you're just taking derivative, and after finitely many steps, you're going to get 0. So the exponential of delta divided by 8 pi. It's just like the identity minus delta divided by 8 pi plus, and then you're going to stop. If you apply it to the polynomial P, you will stop at certain range where the Laplacian applied k times to P is equal to 0. But in particular, the first term is just going to be P. So let me call it the holomorphic part is determinant of y inverse generating series over all j to the power g, P lambda bar square root of y acting on the right times q to the power h of lambda bar. So this, by the homogeneity condition, this in fact will be just P of lambda bar times the determinant of y, which simplifies with the determinant of y. And it will just depend then holomorphically on the variable in the Hermitian upper half space. And it is just the series we considered to start with. So we have exhibited this series as the holomorphic part of a function that transforms like a non-holomorphic modular form, and that's what we call a quasi-modular form in its generality. Okay, great. Now, so that's maybe like the corollary that they said of the theorem. Now let me somehow still like not satisfactory. We can ask.
What does the non-holomorphic part look like?
So the non-holomorphic part, well, you have this polynomial P, and then you're going to compute its Laplacian. You get a new polynomial P1, and then.
Assume it's simpler or not? Huh?
Okay, so it depends. Okay, so if it really depends how you start with P. Let me say that in a second. Okay, I'll answer your question. So I guess the question is how far is this let's say for PC2, so this theta of PC2, how far is theta of PC2 from being just an honest holomorphic modular form? So if you believe this theorem, it depends on how many times you have to apply the Laplacian to P to get 0. That's going to determine the non-holomorphic part. But it turns out the answer also depends on C2 and where it lands in the Lefschetz decomposition of the boundary. So that's the next thing I want to talk about. So this map, what we have done is we have defined a map from the homology of the boundary, or let's say the Hodge homology of the boundary, to this space of polynomials f and g. And now we can put them together in a direct sum from G0 to n. And now really the nice fact that appears here is that this also has dimension ng squared, the same dimension as this. So these two spaces have the same dimensions, okay? And this map is injective. So this is an isomorphism of vector spaces, okay? But we can say more. They're both SL2 modules. So this f and g, so if you have a homogeneous polynomial f and g, you can apply the Laplacian to it and get like a lowering operator that takes you from f and g to f and g minus 1. So we just say this has an SL2 action. Then you have a raising operator that takes you from Fn G-1 to Fng. And same thing here. This also has an SL2 action, which is just determined by the choice of a polarization, the ample line bundle on the boundary. And there's a very natural line bundle to consider, which is just the conormal bundle. So on BI, so there's a natural ample line bundle, which you can construct in two ways. First, either like you take the conormal bundle in the Shimura variety, or you can take the polarization determined by H. In fact, the magic thing is that after a constant, these two things coincide. It's like, so a line bundle determines a Lefschetz decomposition, and then so the theorem is that if C2 is primitive with respect to this Lefschetz decomposition, then this PC2 is harmonic. If C2 is, raising operator times primitive, like it's lined in another piece of the Lefschetz decomposition, then PC2 is it's not going to be harmonic, but the Laplacian squared is 0. So the degree at which this P is close from being harmonic is measured just by in which piece of the Lefschetz decomposition C2 lies in. Okay, so we can now make this even more. Yeah.
This is like this, when it's weakly harmonic, it's always weakly harmonic, meaning either Laplacian or Laplacian squared, but not any other eigenvalue. You don't get a mass form. You never get anything.
Right. Exactly. Yeah.
Interesting. Is it Laplacian squared always, or is that just a line bundle? I mean, it's
Laplacian
to have a fourth order operator.
Laplacian. If C2 lands in a higher piece of the Lefschetz decomposition, then you have to apply higher Laplacian. Yeah. I guess this thing continues, but for the sake of time, let me just say, like, the final punchline here is that to this map here, like, was really defined using special cycles. Like, we are taking a cycle C here, and we're associating to it the function which to lambda bar pair this the harmonic representative that I constructed along P lambda bar on C. So this is really the map that's being constructed here, SL2 modules. And so what does it say, is that the special life cycle Z lambda bar will land in, so this is a map from the homology to space of polynomials. If I write it in another way, it's a map from H, the cohomology tensor with F and G. And the fact that it's an SL2, this map was an SL2 representation, says that the Z lambda bar, in fact, is killed by the SL2 action. Which basically means that whether you applied SL2 here on this side or on that side, you get the same thing. So it will lie, so it will admit a decomposition into so this space here will be sum of you can take the Lefschetz decompositions on either side, and so if you take it on the right hand side, there will be the Lefschetz operator applied to the primitive cohomology of LL, And then you can also take it on the other side, and you have the raising operator on this Fn of L prime, the power G minus L. So these are the raising operator on this side. And this is the space of harmonic forms. So the special cycles are at the boundary lie in the subspace of the cohomology. Okay, in concrete terms, what does that mean? It means that if you choose, so I mean, this decomposition is canonical. But now, if you make some choices, if you choose WIL, a basis of the primitive cohomology.
What is this Q?
What is what?
HQ.
Oh, G. Yes. Thanks. If you take a basis of this primitive cohomology, there is going to correspond to it canonically a basis of harmonic polynomials in F and L prime that I will call PIL, such that this Z lambda bar is just a sum from L0 to G of these polynomials raised L times this PIL. And then so these are now just polynomial functions, and now I need a cycle, and the cycle will be just these primitive cycles that also are raised G minus L times using this sample line bundle. Okay, so that's the ultimate decomposition. In particular, the terms that correspond to L is equal to G will be harmonic. And all the ones from 0 to G minus 1 are, they're not going to be harmonic, but they're all supported by cycles that are contained in the boundary. So these are these cycles that we subtract from the Z lambda bars to obtain Kudra's correction. So, punchline. That Z lambda bar minus sum from L0 to G minus 1 of these polynomials times W at L coupled with L to the power G minus L. That generating series is harmonic. And so defines a holomorphic Hermitian modular form. Now, the presence of the fact that this G minus L is always positive basically says that these cycles can be seen inside, can be deformed to the inside of the unitary Shimura variety, so we can see them in the ambient Shimura variety. And this is the correction that answers Kudla's conjecture. Okay, I'll stop here because I'm running out of time. I'm happy to answer more questions. Thanks very much.
You mentioned Shimura's work. He had the notion of nearly holomorphic. That
For modular forms, right?
modular forms probably have these spaces. Well, maybe there's emission spaces. So I'm wondering, you've got these different notions. You've got weakly harmonic, you've got, you decompose this into a holomorphic part and this part. I'm trying to remember what his notion was. And is that where he introduced this e to the minus p over 4?
So this like I found in some notes that he had in Montreal in some appendix where he talks about this, but I think I know which paper. I mean, he has a lot of papers about this, and in fact, the one piece of the story that I still need to understand a little bit better is that we have like this. Let me say it here. I still have a map. No. Okay, I erased it. But there is this like the space of polynomials f and g. It has a map to the space of non-holomorphic modular forms. UGG. And so this has an SL2, or like at least the direct sum has an SL2 action. And I think Shimura defines an SL2 action on this space of non-holomorphic modular forms. And I think my conjecture is that also it's not intertwines these two actions, but I cannot prove it yet. And that's
See, the word non-holomorphic is a very, very non-descriptive word. It's just non-holomorphic. Could be, the point is it's not holomorphic, but something very special. So harmonic, you actually got something very interesting here, that it's eigenfunction of Laplacian to a power.
Right.
He had I'm just asking whether his notion of near holomorphic, or I think it was called near, right?
Is what, sorry?
It up now.
Brunier?
Somebody know? No, Shimura.
Oh.
Almost or near. Yeah, he was. I remember him telling me about this.
Okay. Yeah, no, I don't know it very well.
I have to look at his work. Because I mean, this was all before this Brunier type stuff and Broadcast type stuff, where was the these notions of weakly harmonic mass forms come in.
Right.
Naturally. Yeah. So this, of course, it's very much related in higher dimension.
Right. So, I mean.